So here's where we left off. We're going to substitute this V over R in for the W. Then we're going to clean all this up and substitute some values in for that I. Here we go. Alrighty, so you can see we have a solid cylinder, we have a hoop, we have the hollow cylinder over here, and we've got a cart down here. I'm not going to talk much about the hollow cylinder because that's going to make it, well, in reality, you can get away with just using the hoop and just using the average value of that R, and that's going to be closest for us. You might notice that, hey, that cart, if I roll that cart down the ramp, that looks like the easiest one to do yet. Yes, it is, because there's nothing rotating. Sure, in reality, there's wheels rotating on the cart, but the wheels are usually so small, the moment of inertia is so small, and those have very little kinetic energy, so you can kind of disregard the rotational inertia, the rotational kinetic energy of the wheels. They tend to be so small. And so this is how you can find the velocity at the bottom. So that's not what we're doing, we're just comparing it to that. We're comparing to the whole body rotating. So you notice what we've done here is this is the starting potential energy, translational kinetic energy, a hoop versus a solid cylinder. You can do the basketball one, you could do the bowling ball one as well. And these are the rotational kinetic energies. It's the half times the I, remember it's a 1/2 mr squared because it's a solid cylinder. If it's the hoop, it's just the mr squared. It's got twice the moment of inertia. If this had been the like a solid sphere, like a bowling ball or a marble, that would be a 2/5 mr squared. If this had been like a basketball or a tennis ball, this would be like a 2/3 mr squared. Now, instead of having the W looking thing, remember we substitute the V over the R. So this is where the magic happens, guys. So what's going to happen here is one of the R's cancels out there. And, oh, so I didn't show you this. So that's squared. So that's going to be a squared up here. And that makes that a squared here. So it's not just one R that gets canceled out. They both get canceled out. And not only that, but we're going to divide out by M on every single term we have here. So that's good news. Because some of you might have been worried about you don't have a way to measure your mass of your item at home. Not a big deal. You don't have to know the mass of your item to find out how fast it's going at the end, because when you convert this into the formula for the moment of inertia, the mass actually drops out. You don't have to have that. And so what you end up with over here is, rather than me drawing with my mouse, is a GH equals a 1/2 V squared, and a half times a half is a fourth, so plus a fourth V squared left over, and a half plus a fourth is 3/4, so GH equals 3/4 V squared. Now solve for the V. So that means your V is going to work out to be 4/3 GH, but that's the square of the thing, right? You got to do the square root of both sides yet. So the point is, it's not really that big a deal. This is the theoretical speed that your solid cylinder should be traveling after dropping that vertical height down your ramp. That's the translational velocity, which now you can actually time that thing. You could set up some things at the bottom of your ramp, and you could time that thing at the bottom and to see what your x per t is and see how close it really is to that value. And secondly, you could convert that very quickly into an angular speed by just doing the V over the R to see what the angular speed is, because that's what I also want you to do on this lab. Not only find the translational speed, but find the angular speed. And then compare it to what it really is over here. Okay, so you're going to do an actual timing of the thing. Now, let's say if you don't want to measure this over here, how could you find what the speed would be? Well, remember, the other way to do this is you could actually do the whole length of the ramp divided by the time, but remember, that's an average velocity. So then if you wanted to change that average velocity into a final velocity at the bottom, Remember, you just take it times 2. Because remember, your average velocity is your v1 plus your v2 all over your 2. And your v1 is 0 because you started at rest, because that's what I'm telling you to do, start at rest. So to find your final velocity at the bottom, it's just 2 times your average, which is that length over time. That would be the other way to do this. So you could actually still use your table as your ramp, and you'd only have to time how long it takes to get that entire length. You'd have to know your length of your table, measure it in some way or another, whether you're using your notebook paper or whatever you're using. You're going to have to know the length of that thing and time it across there. But remember, when you find that average velocity, you got to double it to be the velocity at the bottom, or time that thing at the bottom of your ramp, however you want to do that. Because you want to, this is a theoretical velocity, guys. That may not be the reality of it. We want to see if reality is actually, because we don't, being at home like this, we don't have a lot of experiments. You got to actually have some things involved. You can see if the theory actually is true, if it actually works out that way in real life. Okay? So this is a lab we can actually do to see how well your prediction matches what it is in real life. Alrighty, so down here it's the same idea, guys. The mass all cancels out. You don't need that. This is a v squared, and that's an r squared, so your r cancels out. And I've got a half v squared plus a half v squared. What's a half v squared plus a half v squared? A v squared. So there you go. Well, that's even easier if you did the hoop one. So the hoop one is simply the square root of gh. I didn't screw anything up, did I? Nope, not this time. A half times a half is a whole. There you go, guys. So what if instead you wanted to do the solid sphere? Well, that just is a 2/5 over here. The math isn't that much harder. It's a half of 2/5. So half of 2/5 is 1/5. And you got to add that to your half and so on. Okay? So the math really isn't all that bad. Okay, so let me scrap all those drawings. So those are gone. And so the author's gone ahead and done all this work for you. So there's your 4/3. There's your v equals the gh because you took the square root of both sides. And that's if you went and did the hollow cylinder spot on with the inside and the outside radius and so on. And with dropping at 8 centimeters, so of course the solid cylinder was the fastest. It's got the least moment of inertia of all those 3 items. The hoop with all the mass on the outside was the slowest, so no big surprises there. Okay? So that's in theory. You still got to test this stuff out, guys. Okay? So this is going to be a full write-up. I guess in your hypothesis, you can say, hey, which is going to be the fastest at the bottom? So you could put that in your hypothesis. But your conclusion talks about how does your actual speed at the bottom compares to your theoretical speeds over here. Okay? So that's your write-up that you need for the object rolling down a ramp lab. The speed of the object rolling down a ramp lab. So theory versus practice. Let's wrap this sucker up. Hey, do your theoretical values match up with your measured values? Well, that's what you put in your conclusion. How well do they match up? So they don't. Are they close? Why are they off? Explain why they're off. Explain any kind of errors that may have crept into there. Why are they different? Is there any kind of friction? Is there any bumping going on the ramp? Any bumping at the bottom of the ramp? Switching from the ramp to another surface? Is your time device, maybe using a camera, not very good? Is your hand time? Is your thumb too fat for your own phone? And if you're using that for a timer, I don't know. That's what you're going to have to talk about. Is your height not exactly what you claim it to be vertically? Because this is the vertical height the author is talking about, not the length of the ramp. Because remember, on your MGH, the H is not the length of the ramp, it's the height from the bottom surface that you're going to. Okay? The bottom of the ramp. So something to think about, if you had a ramp that went back up, how high would it go? Would it go to the same height that you rolled it down from? What would be, so what if there was no friction? So these are questions we're going to try to answer in class after when you come back on Tuesday. What if there's no friction? How would the results be different if there was no friction on your ramp whatsoever? I'm going to leave it at that. You guys got any other questions? All right, well, that's your lab that you guys are going to do for Tuesday. Yep. All righty. Have a great weekend.